Welcome grade 12s to this physical science lesson, and today we are going to look at rate of chemical reaction. It is a consolidation lesson. So we're going to draw on what we've learned in the past. We're going to look specifically at questions that you might get in the future, and we're going to use vocabulary, our understanding of vocabulary to unpack those questions and see exactly what we are being asked and how we're going to answer them. Right, so let's look at the first question. And the first question is about two experiments that are being carried out. So two experiments are carried out to investigate, let's have a look here, to investigate one of the factors that affects the rate of reaction, and that is between magnesium and dilute hydrochloric acid. The balanced reaction is shown below because, of course, we always need balanced reactions. Magnesium solid with hydrochloric acid makes a salt, magnesium chloride, and hydrogen gas. In experiment 1, they're telling us a certain mass of magnesium ribbon, let's look at that word ribbon, reacts with excess. Excess means that there's a lot more than is needed for the reaction to take place. So it means that the magnesium then is the thing that is a restricting agent. In experiment 2, magnesium powder is used, so there's something different there, of the same mass of magnesium ribbon. It reacts with the same volume of excess hydrochloric acid, and the concentration of the acid is the same in both experiments. So what they're telling us here is that there is a change in the magnesium and how it looks. So there's the ribbon. So magnesium ribbon, and in the second experiment they're changing that to a powder of magnesium. However, the mass of that remains the same, so magnesium mass is the same. Also, the concentration of hydrochloric acid remains the same in both experiments, as well as the volume of hydrochloric acid. So the volume of hydrochloric acid remains the same. The thing that is changing is the state of the magnesium solid. Right. The first question that has been asked in this exam question is define reaction rate. So there are 4 different types of definitions that I've put on the board. You need to choose one. You need to learn it off by heart. It's easy marks. So let's look at it. What is the reaction rate? Well, it is the change in something per unit time, because rate is referring to time frame. So in this case, change in concentration of the reactant or the product per unit time. The second one that you could use is change in the amount or number of moles of reactant or product, and again, per unit time. The third one, change in the amount of volume of the product that is being produced per unit time, and change in the amount of mass of reactant which is being used up per unit time. You choose one that you're going to use. Our next question for this investigation, to do with the magnesium solid reacting with the hydrochloric acid, write down which one is the independent variable. Now, the independent variable is that thing which is changed in the experiment, and it is a known change. And this one is the surface area, because we started off with ribbon and the second experiment used powder. So that is a change that we know about. The next question here is, what is the control variable? The control variable, you have a choice of 3 to write down here. Control is what stays the same. Well, we know that the mass of the magnesium stays the same. Also, the concentration of hydrochloric acid stay the same. They specifically told us that. A third thing could be temperature. Now, they didn't mention anything about temperature, but they didn't say it's changed. So if it doesn't change, it means that it does remain the same. So these are the three constants in this particular experiment. Following on from these questions, we have a question that is going to require a calculation. The change in mass of magnesium, so it's a change in mass of magnesium, is calculated and recorded in 2-minute intervals. So that affects this graph on the x-axis, the time axis. And this happens for both experiments. The results obtained are shown in this graph. And there we go, there's the graph. You can see experiment 1 and experiment 2. Calculate the volume of hydrogen gas produced in experiment 1 from the time interval t equals 2 minutes to the time interval of t equals 10 minutes. Now, they are asking for hydrogen gas. There we go. How much hydrogen gas? What is the volume of hydrogen gas being produced? We do not know that. They have not given that to us. What they have given us is a graph of the mass of magnesium. So we need to start at that point. We need to start with the mass of magnesium. We know according to our equation, our balanced equation for this reaction, that there is a ratio of magnesium solid to hydrogen gas that is being produced. So we are going to use that as our key for finding the answer. So we take our mass of magnesium. Now they say between t equals 2, there we go, t equals 2. We read it off the graph. We're dealing with experiment 1. They tell us experiment 1. So there is our mass, 2.6 grams of magnesium that we start with. They tell us that the time interval is to 10 minutes, and so if we read that off the graph, whoops, it's a bit skew. If we read off the graph, we see that our second reading at t equals 10 minutes is 0.2 grams. So the change in magnesium mass, the solid, is going to give us a number of moles that is being produced, and that will then link into the hydrogen. So let's have a look here. Change in mass is 2.6, subtract 0.2 grams. That's what we've read off the graph. We get an answer of 2.4 grams. That's the change in mass of magnesium. We pop that into a formula. N is equal to mass over molar mass. Because N is the number of moles, we need to get back to that. That's our common factor. So 2.4 over 24, that 24 comes from the periodic table. It is the molar mass of magnesium. Right, and that gives us an answer of 0.1 mole. We have to do something with that 0.1 now, and we're going to look at the mole ratio. So we have got the number of moles of hydrogen formed is the same as the number of moles of magnesium used up. So number of moles of hydrogen equals 0.1 mole. We want to find out the volume. That's what they're asking us for, the volume. So volume is equal to number of moles times the molar volume, which they have given it to us in this question. 0.1 then times 25 is equal to 2.5 decimeters cubed of hydrogen gas that is formed. Our next question is calculate the initial mass of magnesium used if the average rate of formation of hydrogen gas is this amount here. And you can see that it is a measure of moles per second. The average rate then would be delta N, change in number of moles over change in time. This is a formula that you need to know. It is not on your information sheet. And we substitute in. So they have given us that rate. They have given us time because we can see it on our x-axis on this side. And they tell us that it is in 10 minutes. The trick here is 10 minutes does not match the unit, which is per second. So we have to convert that 10 minutes into seconds by timesing by 60. We work it all out and we get an answer of 0.125 mole. What are we going to do with that? We need to calculate the mass of magnesium that we start with. Again, our mole ratio is very important. It is a 1-to-1 ratio. That means that the number of moles of magnesium that we start with is the same as the number of moles of hydrogen that is formed in that time. And we then substitute our values into the equation. The mass of magnesium equals number of moles times molar mass. Molar mass, again, from our periodic table. And once we calculate that, we get an answer of 3 grams. Right, I hope that has helped you, grade 12s, to work through these type of stoichiometric problems. And we are now going to take a break. Welcome back, grade 12s. We are consolidating rates of chemical reactions, and we're looking at exam type questions that is going to help us just tune our mind to be more precise about how we answer these. This question, question 2, is about antacid tablets. Now, when you have been eating too many slap chips and you get a sore tummy, it means that your stomach is producing too much hydrochloric acid. And the question reads, the calcium carbonate in an antacid tablet. So you take one of these tablets, and what it does is it reacts with the dilute hydrochloric acid within your stomach. And this is the balanced reaction, calcium carbonate reacting with hydrochloric acid to form a salt, calcium chloride, carbon dioxide gas, which is why you burp so much, and some water. But at the end of this reaction, there is a clue. It tells us that delta H, or the change in enthalpy, is smaller than 0. In other words, it is a negative value. The first question that they ask about this is the above reaction exothermic or endothermic? And give a reason for your answer. Well, because delta H is smaller than 0, it is a negative, it has to be an exothermic reaction because the change in enthalpy is negative. Our next question, an antacid tablet of mass 2 grams, so they're telling us that it has a mass of 2 grams, is placed in the hydrochloric acid. After 30 seconds, the mass of the tablet was found to be 0.25 grams. What are they giving us? They're giving us a change in mass of the reactant. So calculate the average rate in grams per second of the above reaction. Average rate is minus delta M over delta T. Why is there a minus there? Well, from our previous knowledge, we know that when we are measuring the change in mass of the reactant that's being used up, the graph that we're going to get is going to be looking like this. It has a negative gradient. So when we work out the average rate, there has to be a negative placed next to that formula. We need to know that formula. It is not given to us. When we substitute in, we then substitute in 0.25 grams, subtract 2 grams, and we get a negative answer for that. That's in this bracket here. And negative times negative will give us a positive rate of reaction, and it is worked out as 0.06 grams per second. The next question is an interesting question because it's about percentage that actually takes part in the reaction. So it reads, the antacid tablet contains only 40% calcium carbonate. Another antacid tablet of mass 2 grams is allowed to react completely with HCl, that's the hydrochloric acid. Calculate the volume of carbon dioxide, that's CO2 gas, that will be collected at standard temperature and pressure. and assume that all the carbon dioxide produced is from the calcium carbonate. Right, so again, we need our balanced equation, and we need to have a look at our mole ratio. So the two substances that are in this question are calcium carbonate, the solid, and the carbon dioxide gas that is made. The ratio between those two substances is number of moles of carbon dioxide is 1. That will be produced from 1 mole of calcium carbonate. We need to calculate the number of moles of what we are given, and what we are given is calcium carbonate. Now, the whole tablet does not react. The 2 grams does not react completely. It is only 40% of that 2 grams that reacts. So we have to calculate how much is 40% of that 2 grams. Here we go. I have done it in this weird cloud on the side. 40 over 100 is 40% times 2 grams, and that gives me a result of 0.8 grams. That is the amount of calcium carbonate in the tablet that reacts. It's the 40% that reacts. So in place of placing a 2 gram in that mass space, I will place 0.8 grams that reacts. Divided by the molar mass of calcium carbonate, you need to calculate that from the periodic table, and you get an answer of 0.008 moles. Now, what must I do with that? Well, I have to now convert that number of moles into the volume of carbon dioxide that is produced. So we know the ratio is 1 to 1, and all I have to do then is pop my values into the formula. Volume of carbon dioxide is equal to number of moles times the molar volume. 0.008 times the molar volume, which they have given me in the beginning as STP, because at STP I know that my volume of gas is going to be 22.4. I times it out, and then I need to round off to a 0.18 decimeter cubed of carbon dioxide, which is produced. This question is a lovely question. It is about the Maxwell-Boltzmann distribution curve. So if you look at the slide, you'll see the Maxwell-Boltzmann curve. There are 2 curves, curve A and curve B. This represents the number of particles and their kinetic energy in a reaction. There are 2 different reactions, one at one temperature, one at another temperature. It tells you there that it represents the number of particles against kinetic energy for a reaction at 2 different temperatures. Now, what does this P line represent? If you know your Maxwell-Boltzmann distribution curve, you will know that at this point, that is where the particles will have enough kinetic energy to make the reaction happen. And so that P line represents the activation energy. So for a reaction to happen, the particles have to have the same amount or more kinetic energy as the activation energy. I have written here the number of molecules have sufficient or more than the sufficient kinetic energy to make effective, the word is effective, collisions. So which curve then, A or B, was obtained at the higher temperature? So with the Maxwell-Boltzmann, we know that if the temperature increases, that whole curve is going to shift to one side, and it shifts to the right-hand side, showing that there are more particles that have sufficient kinetic energy. So B, curve B, is the one at the higher temperature. Explain in terms of the collision theory how an increase in temperature is going to influence the rate of the reaction. So at a higher temperature, there are going to be many more molecules that have a higher kinetic energy. When there is a higher kinetic energy, there is more movement or more particles that can move faster. So there are more molecules that have a kinetic energy that is equal to or greater than the activation energy. That means that more effective collisions happen per unit time, and effective collisions mean that the molecules are at the correct orientation. This increases the rate of reaction. So there we go, reaction rate increases. Right, grade 12s, I hope that this has given you a better insight into how to answer questions around the stoichiometry of rates of reactions, how to calculate the number of moles, how to calculate mass of a reactant used up, how to calculate volume of gas produced, and also how to use your words very particularly to answer the collision theory questions surrounding the Maxwell-Boltzmann distribution curve. That is us for now. Have a good day.